Smarter doesn't sacrifice energy efficiency or sustainability for higher performance. Lenovo has been leading the world in liquid cooling technology for over 10 years. Find out how you can increase performance while reducing energy at lenovo.com/Neptune. That's NEPTUNE.
And now with Edge to Core, you're looking at a whole enterprise fabric where everything wants to be not only a computer, but an intelligent computer.
And it's all about decentralization.
I believe what you just said is a very critical piece of the dynamics, and that is the balance between decentralization and centralization. And certainly with the advent of AI, which is sort of what we are at the dawn of that age, basically all workloads are going to be AI enabled. All of them are going to be rather decentralized in some fashion, and all of them are going to be customized because we are in post-Moore's law.
From Orion X in association with Inside HPC, this is the @HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hi, Shaheen. As always, it's great to be with you.
Excited to be here, Doug, and also because we are finally going to tackle a very big topic that we've talked about and touched on, but haven't quite met head on.
Yes, and that is HPC Software. And our plan is to have this be a kind of a kickoff discussion that will be followed by more discussion, more specifics, getting into different aspects of software and HPC, and also some guests and experts in the field. But we thought this would be a good opportunity to talk kind of give our overall perspective, kind of create a bit of a framework for looking at HPC software and also some of the key issues, challenges in the area.
Yeah, I think it's time to do this, and I'm excited for us to do that.
Well, great. So in thinking about what we would talk about today, the phrase came to my mind, software is eating the world. I forget the creator of that phrase. It's one of those paradigms of IT. But it occurred to me, is software eating HPC? Is that a valid premise for discussion?
I think that's an excellent question because I don't believe software is doing any such thing.
Either at HPC or anywhere else.
Actually, to be fair to the quote, the growing importance of software is unmistakable.
Yeah.
And certainly in that sense, you could phrase it in any way you want. But if you're trying to indicate that software is a really, really important thing, for you to then say it's eating the world is not a bad way of getting attention and making it like a controversial comment. However, I believe what actually is eating the world is digitization. And digitization is an integration of hardware and software is a component. I'm reminded of the famous Alan Kay quote that if you're serious about software, you build your own hardware. I believe It's a quote like that. And that indicates just what is all going on there in my view.
By the way, it was Mark Andreessen who said software is eating the world. I looked it up. And I love your point that really it's the digitization of all life that applies across all of IT, particularly HPC, but it's almost a digital twin of the world that we're creating.
Absolutely.
And of course, it's hardware and software. So
absolutely. And in fact, increasingly, the hardware is a very, very important piece of it. On the device side, that's very clear. Your mobile phone is an example of that. Your smart appliances are an example of that. And actually, that's not a bad segue into what is really going on in the IT world. And as you have heard us talk about and others have as well, I believe we are in the fourth phase of information technology. We've gone from terminal mainframe to client server to mobile cloud and now to edge to core, or you could say edge to core to cloud, edge to data center to cloud. And as you go through these phases, the system architecture and the application architecture have a symbiotic relationship and they nudge each other forward. The technology enables things, application requires things, and provides opportunities to optimize that the hardware then does. And then as you move that forward, sooner or later, you're going to get into a whole new application software regime. Terminal mainframe was monolithic applications, it was all on a mainframe and interacting with a display terminal. Client server decomposed that into 2 tiers and then 3 tiers and then multi-tiers and then peer-to-peer. When you got to mobile cloud, that peer-to-peer elasticity of applications became a lot more important. And now with edge to core, you're looking at a whole enterprise fabric where everything wants to be not only a computer, but an intelligent computer.
And it's all about decentralization.
I believe what you just said is a very critical piece of the dynamics, and that is the balance between decentralization and centralization. Because if you push either of them too far, they have diminishing returns and they cause complexity that then gets in the way. If you decentralize too much, then you sort of become the 10,000 chickens kind of a model where you have a lot of modularity, but then you also have a lot of complexity and change management and dependence management and just orchestrating all of them. But if you get too monolithic, then you become too restrictive and too difficult to modify things. So the balance between the flexibility of modularity and the efficiency of centralization is really a very big recurring theme in all of IT.
Well, I love that point. It's kind of a yin yang thing. I mean, having come in, really begun my work life just at the dawn of the PC revolution, and I just saw that as you're just putting so much computing power in the hands of the individual, which fosters and nurtures all sorts of unforeseen, creativity and individual initiative. But then you move toward a chaotic situation where there's no central control. If you're running an organization, you have to have some sort of a management, right? So it kind of moved back and forth, but that seems to be the constant back and forth here.
Yes, yes. In fact, in a kind of a hopefully a funny way, it reminds me of the Get Smart TV series with Maxwell Smart, and if you remember, it was control versus chaos.
That's it. Gosh, I should have thought of that exactly.
So yeah, the control agents and the chaos agents,
Yeah.
and that always kind of reminded me of the challenge of information technology data centers and how do you balance the two?
Right, exactly. Okay, so looking at HPC software, it does present its own unique characteristics that you don't see as much of outside of HPC. Isn't that true? And the big issue is this extreme parallelization that you see with these clusters. You've got tens, sometimes thousands of
Right.
servers and orchestrating all of the work that they do. That's what it's all about.
Well, when the market segment starts with the words high performance, right?
Hmm.
Your assignment is pretty clear. Get performance, make it go fast. So what has traditionally distinguished HPC from the rest of computing is an overriding focus on extracting performance from every resource that you have. The second one really is the nature of the applications themselves, right?
Yeah, and I think this is a really interesting point. Go ahead, please. Yeah.
Yeah. So, again, if you look at the history of computing with management information systems and data centers and kind of, the glass house of a mainframe thing, those are all transaction processing systems where the
Mm.
focus was on response time across a very large number of users. And online transaction processing, OLTP, became the moniker to represent that sort of an application. And then how you optimize that application was focused on response time. Databases were involved. Banking debit credit application was an example of such a thing, and it actually led to the benchmarks that were important in that world: TPC-A, TPC-B, TPC-C. Those were like that. Then we went to queries, decision support systems, data warehousing. That eventually became business intelligence. You would take your live database and you would replicate it, and then you would run queries on it to generate reports, to ask what if questions. And that eventually became, how do I really surf my database for insight? As the size of those databases began growing, you had new kinds of databases, unstructured data, columnar databases, other ways of trying to extract performance for those queries, but it's fundamentally a different mode of computation, if you will. HPC was simulation, numerically intensive, analytics, and often guided by a scientific engineering framework or physical laws and formulas. And then when visualization and audiovisual processing came about, that sort of wanted to be its own thing as well, because now you had to display the results in a kind of a visual graphics processing. So graphics processing became one. So that became like the fourth one. And then you needed to communicate. So communication became the fifth one. So over time, all of these have kind of become more and more morphed. And certainly with the advent of AI, which is sort of what we are at the dawn of that age, basically all workloads are going to be AI enabled. All of them are going to be rather decentralized in some fashion, and all of them are going to be customized because we are in post-Moore's law world. So that's one way to look at it.
But the unique requirements to be an HPC software programmer, Sheen, is this a particularly or notably high level form of programming that takes extra skill training than more mainstream forms of programming? Or is it just unique in its own way, just requiring different skills, but it isn't necessarily more difficult? If you take into account OpenMPI APIs, this helps with the whole process of achieving that parallelization that's required here.
So I believe as the software hardware stack has grown, like I like to say, there was a time when you had hardware, you had OS, you had disk, and you were done. And now what used to be disk is this universe of hardware and software called storage and persistence and all manner of how you manage data. And it's highly complex. What used to be the OS is now a universe of software that goes from hypervisor to operating systems to container management to provisioning, orchestration, microservices, compilers, all and on, right? And then what used to be the hardware is now a universe of complexity with chiplets and accelerators and FPGAs and this, that, and the other. There's almost like a big bang in IT where we started with monolithic and every day it just becomes expanded into more and more things that you have to put your arms around. And as that has happened, so has the specialization. So therefore, I believe it's the same kind of complexity. It just depends on where you're focusing on. But if you rewind the clock back to, let's say, 30 years ago, then it was the case that HPC software professionals kind of needed to know more about science and math and numerical analysis and how to extract performance from computers in a way that was really different. And you could argue that required a broader background than traditional computing. I don't believe that's the case anymore. I believe that the complexity of software is so broad right now and so scattered that there is an opportunity, in fact, to bring all of that expertise under one roof and to integrate it in novel, good ways.
The biggest system in the world, most powerful system in the world, Frontier exascale system, 70 cabinets, 8 million plus cores. How to make that system work in concert seems like a freakish task.
Yes, it sure is. And that's a really good point, too, because I used to say that systems like that are a monument, not a market. And if you're building a monument and if it's a one of a kind, then you go make it work and it's a one of a kind thing. But it's not one of a kind anymore. And in fact, when you hear Google launching a supercomputer with 26,000 latest generation GPUs, that thing looks pretty similar to Frontier. It's not as big, but it's right up there. And when you look at what OpenAI is doing, and when you look at what various companies are trying to do on-prem, there is definitely an unmistakable trend that what used to be just a lab environment, a supercomputing site, is now becoming a lot more required and accepted in the commercial world. And AI is causing that. But that's another convergence that's happening that says, maybe the ability to run workloads across this massive technology is more of a requirement generally than just a special case.
Well, in fact, HPC, of course, is increasingly adopted in the enterprise, and HPC is helping to drive the whole AI revolution, which is exploding in the enterprise. So this must have major implications for the software that's going into these systems.
I think we've talked about this on this podcast quite a bit, that at least two of the disruptions that have been driving a lot of things, besides kind of edge to cloud, where everything wants to be a computer, is AI, of course, and post-Moore's law. Because we are post-Moore's law, you can't just wait 9 months or a year and you just go faster. You have to do other things. And what you do is architectural, and what you do is to take your increasing transistor density and use it in novel ways. And then because AI is a brand new environment, that means new algorithms, new applications that aren't yet written. So you actually could write them on new novel hardware. And it turns out you've got tens, if not more, AI chips that are coming. And then you have chiplets and tiles and increasing fabrication density. So all of those absolutely point to new ways of doing applications and optimizing software, and it's exploding in its own way.
Yeah, it occurs to me, and maybe we're somewhat guilty of this, but if this is our first real foray into talking about HPC software, to me, it's always been much easier to talk about the hardware side. I mean, hardware is quantifiable. We can talk about flops and storage capacity. Software seems more amorphous. It seems a realm that's hard to get your arms around. So I think what will be great for us is to bring in various HPC software practitioners who can really help us dig into what that world is like and the various projects they're working on and the challenges they face.
Yeah, that absolutely. I mean, we've covered storage, we've covered compute, we've kind of touched on interconnect and networking. So those are the three pillars of
Mm.
computing. Memory management goes right on top of compute. Fabric software goes on top of networking. Volume management, file system, all of those go with storage and persistence of data. But then you can also separate them into system management, workload management, development environment, federated computing, especially as you go beyond a particular site into more of the network outside of the facility. Every one of those is a universe of complexity and insight that we should track. And as you look at development environment and workload management, I talked about microservices and compilers and libraries, but you've got API libraries, communication libraries like OpenMPI, OpenMP, math libraries, visualization libraries, package management. How do you actually build these software packages in a way that the dependence management and performance and actually suitability to run on your particular software, because now you've got different technological bases with different hardware way down at the bottom of the stack, debuggers, performance analyzers, installation management, change management, right? User interface, all of those are just, we're going to be busy. We're not going to be done soon.
Excellent. A great roster of topics right there. So
Run hot, stay cool, save energy with the world's #1 provider of supercomputers according to top500.org. Lenovo Neptune systems power through the most compute-intensive workloads with over 95% heat removal efficiency and up to 40% lower power consumption. Neptune delivers higher performance in a whisper-quiet, compact footprint so you can achieve a faster time to answer. Visit lenovo.com/Neptune to learn more. That's NEPTUNE.
you know, all of this is in the service of developing increasingly capable, increasingly powerful software programs in the HPC realm, whether it's scientific computing or other areas, Shaheen. What are your views on where this evolution is really taking
We're doing all of this for some reason, you're saying.
place? Yeah, I guess that's what I'm trying to get at.
Well, I think that's an excellent point, too, that when you look at who the constituents are in supercomputing, you obviously have the programmer, the sysadmin, but you also have the end user.
Yeah.
And of course, you also have the buyer, the people who actually like pay for all of this stuff. So as it relates to the end user and the different scientific disciplines, the disciplines that have historically emerged as eligible or amenable for numerically intensive computing were obviously science and engineering, where there was already a scientific formula that would govern the behavior of whatever it is we were studying and would allow us to have a numerical method to get to the answer. What are those? Structural analysis, fluid dynamics, computational chemistry, drug design, seismic processing, reservoir modeling. And all of those included some ISVs and commercial applications that emerged over time to really consolidate what was being done by the research community. And it led to what some folks would used to call the nifty 50. If you had those 50 applications, you really could play in this market. What we have seen is the importance of numerical simulation and modeling into business processes, not just kind of natural phenomena. So that is definitely pulling HPC into new areas. And then, of course, we've talked about AI, and AI is like coming to make sense of these things in a predictive way, because if you have the answer and you have a lot of experiments where you know what the answer is, you can feed that and then come up with a black box that will, and hopefully less of a black box over time, that will now be able to predict some of the answers when you don't have a formula. So I think we are seeing AI be used to advance science, like we've talked in the past with many of our guests. And that is one of the reasons why I think HPC is coming into the enterprise. And if you are an enterprise and you're trying to build an AI group or an AI capability, what do? You go and buy hardware that looks suspiciously like HPC hardware, and you hire people who look suspiciously like HPC people. And at some point, you're going to realize that, actually, I do want HPC people because they have the right background, they understand the formula, understand this, that, and the other. So I think that's moving HPC into new realms.
Nice. All right, Shaheen. Well, as always, great to be with you, and we'll look forward to our next time.
Absolutely. Looking forward to it.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The At HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.